Mic check. Good afternoon, everybody. It's a nice afternoon. So I'm here to talk about hitless software upgrades. The last time, my phone upgraded, I downloaded the software and it just asked me to wait till the night, and it auto upgrades itself. It's no voice calls at the night, nothing going on. I wish switch upgrade is as simple, but unfortunately, switches are always switching packets, and TORs especially, right? They're always switching packets. So it's going to be extremely challenging normally to upgrade software and at the same time keep switching packets and seamlessly transition from the previous software to the new software. And this has been a focus area for us for a while now. And we have been doing this, of course, in traditional Google's notes. And now we're trying to look at SONiC and say, how can we do this better at SONiC? And I'll tell you a little bit about why this is challenging. Thankfully, today's ASICs, switch ASICs, come with a headless mode of operation. So you can basically disconnect from the CPU, keep switching packets, continue as you're programmed, and then when the CPU can come back and connect to you without a hitch, right? But the difficulty lies in making sure that what was programmed by the previous software, the new software comes, learns what was programmed, and seamlessly can program on top of that. The previous software would have filled in so many tables, entered a lot of entries across different tables, and some tables, the order in which you enter things matter. And a lot of that state information is present in the old software. We now have to seamlessly transition that to the new software. And often this ends up not only glitches when you're upgrading, but even in issues that are latent, that are not known. Nothing happens, you smoothly upgrade. And later you're sending in a new configuration to the switch or a new route to the switch, and the thing blows up, right? So we want to make sure that this is seamless. We also want to make sure that post-transition, everything is the same way as in the previous software, right? That's one of the challenges. And the other challenge is that, given all of us are deploying switches, multiple switches, you generally tend to have switches with different software versions running around. And you have your latest shiny version coming up, and now you want to upgrade this. As you transition, most of these issues depend on from which version you're transitioning to which version, right? And depending on the previous version, depending on the new features that have come up in the new version, and also depending, unfortunately, on a particular switch, what state it holds. The first switch may be fine. You go from X to Y, and switch A goes fine, right? You accelerate the upgrade process, you roll it out to 100 switches, and now 20 of them don't upgrade well. So how do you figure this out? How do you make sure that you can upgrade your software without worrying about it, right? And that's the area that we've been working on for a while, and we are trying to, as we design a process here, and we are trying to make sure that the previous process that we have been using in the SONiC community continues to work. We want to make sure it's backward compatible. We want to make sure that we improve the situation. So we are asking for feedback. We are started a working group with this focus, and we are inviting more and more members about, hey, how did you do switch upgrade? What tricks? And today in the industry, and as different deployment, different customers upgrade switches, we see that everybody has some tricks up their sleeve. They upgrade and they do certain different commands through bash and scripts and et cetera to make sure that it works every time. And they discover glitches and they make sure that, hey, the remedy is added in, and so on. And here we are trying to make this a very streamlined process, make sure that this works 100% of the time. And Akarsh will carry forward from here talking a little bit about the design principles that we have implemented and how we are going to take it forward. And through this process, I want to basically iterate that we are going to be backward compatible. We continue to use the previous one. And as we smoothen our transition into the new one, we want to take as much feedback as possible from the community, from all of you who have been doing software upgrades seamlessly, and ensure that we incorporate all those learnings into this process. And hopefully, software upgrades on Switch is just like a push of a button.
Thanks, Bhagat. So my primary focus today would be warm boot orchestration. So what changes we want to bring to warm boot orchestration, and something about config and application DB schemas. So today's SONiC supports both Docker upgrades and Switch upgrades. The Redis DB is backed up, application-specific information is backed up, components reconcile, and they come back up. SONiC already has a warm boot orchestration process, and we are proposing another warm boot orchestration process. And like Bhagat said, the proposal is to be backward compatible. So what we are proposing is that we have a single daemon to orchestrate shutdown and monitor reconciliation. Now, we already have a state machine in the components for warm boot up. Now, if we also introduce a state machine during shutdown as well, this daemon can monitor these states and take actions accordingly. And if we have this state machine, then we also have an opportunity to send common notifications for all components, as opposed to introducing custom notifications per application. Now, the proposal is also to have a generic and flexible framework. So the proposal is to have a registration-based design where each application tells this orchestrator what needs to be done for that application at different stages. And the plan is to leverage the SWS's common library so that we can create a pub/sub model and thereby also concentrate on performance. So the proposed shutdown sequence is a multi-phase sequence where all components of the switch stack will go through these phases in parallel. So phase one is sending a freeze notification and waiting for that component to become quiescent. Let me explain quiescence a little bit. Quiescence means that the application has stopped generating new events, but it will continue to serve existing events. So what will happen is when you receive a freeze notification, an application, if that has periodic timers, will stop those. It will stop exchanging information with external components so that it can no longer modify the state of the switch. But it will continue to serve existing requests. So in other words, it's like I will not ask questions, but I will continue to answer questions. So what will happen is at one point of time, the entire switch will become quiescent, and therefore the switch state will be stable. At that stage, we can trigger state verification that ensures the consistency of the switch at that time. This stage is optional. In phase 3, we can trigger checkpointing. Now, since the switch state is stable and consistent, each component can save their information on the persistent file system or DB, wherever they like. And now you can actually start to shut down applications and perform reboot. So this is a generic framework for all components using a registration-based design where each component shares its name, Docker name, whether the orchestrator needs to wait for it to become quiescent, whether the orchestrator needs to wait for it to complete checkpointing, and whether the orchestrator needs to monitor the reconciliation status. So here's what the flow diagram looks like for core components like SWSS syncd that actually serve requests from all the components of the switch stack. So phase 1 is send freeze. They stop generating new intents. They complete processing current requests and also continue to process requests until everyone else has become quiescent. And once there are no more requests, they report their quiescent state in the DB. And when all applications or all switch stack components have become quiescent, the orchestrator that we're calling is called NSF Manager. We'll move to the next phase, optional state verification phase, where all components verify their internal states and report that they are in a consistent state. Once the switch reports that the state verification is successful, it moves to a checkpointing stage where each component now saves its internal state and updates its state to checkpoint. Now, the NSF manager can monitor these QSN checkpoint state and decide whether it needs to move forward or not. And finally, it will prepare and reboot the switch. Now, for applications, we can actually optimize these three stages into a single stage where an application receives freeze. And when I talk about application, it's mostly boundary applications that are not dependent on any, on which no one else is dependent. So, for example, TeamD, BGP, these are actually serving external requests. They can receive a freeze request, stop generating new intents, say that they have become quiescent. They don't need to wait for NSF manager. They can continue state verification if required. And they can also, at the same time, save their internal state and report checkpoint. And NSF manager will be cognizant of the fact that it needs to monitor both quiescence as well as checkpoints. So at this point, the application is ready for shutdown. And NSF manager can continue to phase 2 or phase 3, and then prepare and perform reboot. The proposed boot up sequence without state verification, since state verification is optional, is similar to what we have currently. So NSF manager waits for the components that have registered with reconciliation equal to true to complete their reconciliation. Once they update their reconciliation state, it determines that the switch has reconciled, and it removes the warm boot flag. So this is very similar to what we have today. The difference is that this is based on a registration-based design as opposed to monitoring a specific set of applications. Another thing that we can do is that if we enable state verification, we can add additional consistency checks after reconciliation. So before applications can start processing new intents and modify the hardware, we can also verify that the switch is in a consistent state before we can actually do that. Now, the trade-off is obviously it's a longer upgrade duration, but this is generally for applications that are in dev testing. You want to figure out reconciliation bugs. So this sequence can be used at that time, where you wait for reconciliation from all components. Once the switch stack is reconciled, you trigger a state verification. When everyone reports that they are in a consistent state, you then actually send an unfreeze notification so that applications can start generating new intents. I'll go through this slide quickly. So today, we don't have any config and application DB schemas defined, or they're defined in a markdown file. The one problem is that they might not be up to date, and we cannot enforce these markdown files in the org agents themselves. So the problem with not having consistent schemas is that you might generate ASIC operations after reconciliation, and that can modify the ASIC state and cause traffic drops. So the proposal is to introduce schemas, JSON-based schemas, enforce them, and add schema validations in the pre-submit pipeline itself so that we can catch these issues earlier. The next thing is to deep dive into the detailed design of these areas and also extend this design to fast reboot. As Bhagat said, we are looking for feedback, collaboration ideas, and we have a system orchestration subgroup where we are going to discuss this in more detail. Thank you.
Thank you.